design evaluation of sintered chip breakers and throwaway inserts. The research and high-speed photography for this film were carried out by Joseph Gamini Pinto, under the supervision of Professor Joseph I. Elgomayel of Purdue University and John Agnew, Manager Product Development, Adamus Carbide Corporation. This film was partially supported by a grant from Adamus Carbide Corporation, Kenilworth, New Jersey. Metal cutting is one of the most important manufacturing techniques, and it will remain so at least in the near future. Today, numerically controlled and even adaptively controlled machine tools are replacing conventional ones. There is a rapid improvement in tool materials and in the direction of increased cutting speeds. At high cutting speeds, a great length of hot and often sharp chip is produced in a short time. If the shape of such a chip is not controlled, the tool support and the workpiece may become severely entangled in the chip, causing serious delays and even damage to the tool and workpiece, as well as being a hazard to the operator. It is important to produce chips that occupy little space in relation to their weight. This film is concerned with making chips and is produced by the Manufacturing Engineering Laboratories in the School of Industrial Engineering at Purdue University during an investigation of molded-in chip breakers in indexable carbide inserts. The laboratories occupy 20,000 square feet and are equipped with a large number of conventional as well as non-conventional machine tools. They serve as a center for education, research, and training for undergraduate and graduate students, as well as the manufacturing industry and many branches of the federal government. The objective of this research was to design a groove which would break chips over the broadest possible range of feeds and speeds while keeping the cutting forces to a minimum in order to obtain maximum tool life. In all, 18 different groove shapes were studied, and their groove parameters were compared to the type of chip obtained in the cutting operations. In the laboratory, we are approaching the American pacemaker lathe, where we will watch as Joseph Pinto conducts cutting tests for the chip breaker research. This is a 20 horsepower lathe with 16-inch swing and a 6.5-foot center distance. Wear of the cutting tool is mainly dependent upon the forces acting on it during the cutting operation. Therefore, to avoid wear and damage, it is necessary for the chip breaker groove to have a shape that minimizes these forces. As shown in this diagram, a 3-component dynamometer was used to measure the forces in all 3 directions, those from feed, speed, and depth of cut. Here we see the equipment in action. The tool holder is mounted in the dynamometer. As the tool enters the cut, the forces are measured and the measurements are transmitted to the Sanborn recorder, where a permanent record is made. 3 cutting edges of each insert were tested at 2 different speeds, which were recorded here. A statistical computer package was used to analyze the results. In order to see the action at point of cut, a high-speed motion picture camera was used. At normal cutting speeds, it is impossible to see this action. Instead, we see a shower of chips flying in all directions from the cutting edge. Here is the same shot as seen through the eye of the high-speed motion picture camera. The action is slowed down so that we can see the chips being formed. The balance of this film shows how this high-speed photography was used to capture the cutting action of various chip breaker grooves. This engineering drawing shows a typical land and groove type chip breaker. The W indicates width and the D indicates depth. In order to better understand how these chip breaker grooves are used to bend and break the chips, let us first examine what happens when you use an insert that has none and is flat on the top, as shown in the illustration. This is what happens at 235 surface feet per minute and 39 thousandths feet on 1045 steel. Without the chip breaker, the chip flows in a long continuous curl. The curl will break at above 40 thousandths feet. A lower feed, 39 thousandths, was therefore selected as the heavy feed for this research. The light feed used was varied depending upon the insert being tested. The inserts are TNMG 544A and C roughing grades of carbide inserts. The work material is medium carbon 1045 steel. It was learned that velocity has little or no effect on chip breaking. Each chip breaker groove was measured with the Purdue crater measuring device, and an engineering drawing was prepared showing its exact contours. Here we see a typical chip breaker. Let's see what happens when we introduce this insert at the heavy feed you saw a moment ago, 39 thousandths feet on 1045 steel. The chips curl very tightly, exerting tremendous force upon the cutting edge. Tool life is reduced. Also, notice how the chips rapidly strike the cutting edge just beyond the depth of cut. This frequently causes edge chipping on the insert and is one of the main reasons for honing an insert edge. Here is the same insert at 16 thousandths feet. The chip still breaks as it strikes the cutting edge, but the control is not nearly as good as it was at the heavy feed. The forces recorded are very light. Tool life will be good, and chip control will improve as the insert begins to crater. If we slow the feed down even further to 14 thousandths per revolution, the chip does not break at all, but comes off in a long, curling, razor-sharp band, which may wrap around the tool post or control handle of the machine and be very dangerous to the operator. Our objective is to learn how to break this chip, while at the same time producing a looser chip at the heavy feed. Remember these chips. We will look at them again later. Here is an engineering drawing showing a chip groove which is wider than the first groove and also has a wider land. It will produce a more loosely curled chip at heavy feeds. What will it do at the low feeds? When we try this insert at the low 16 thousandths feed, we find that it does not break the chip, but instead produces another long razor-sharp band similar to the previous insert at the lighter feed. This is because the land width is now too great. The chip passes over the groove as though the entire top of the insert were flat. It has now become obvious that if we are going to break the chip at the light feed rate, the width of the land must be reduced. One way to accomplish this might be to use a shelf-type chip breaker similar to the one shown in this engineering drawing. The land is narrow with a long positive angle running down to an abrupt back wall, typical of most shelf-type chip breakers. Again we try 16 thousandths feet. The chip breaks, but the dynamometer records very high cutting forces which will result in early tool failure. Another disadvantage is the very narrow feed range over which this chip breaker is effective. A second method of breaking the chips at the low feed rate is shown in this engineering drawing. Here we have a chip breaker with a narrow land and a narrow groove. At 16 thousandths feet on 1045 steel, the forces are a little higher than they were on the first groove, but the chip control is much better, and it is evident that this groove will break the chips at lower than 16 thousandths feet. The question is, what will happen if we take this groove up to the heavy feed? The answer is not what we might anticipate. At 39 thousandths feet, the dynamometer records very high cutting forces for a few revolutions. Then a section of the land breaks away and we generate a very ragged chip for a short time longer until the entire corner of the insert breaks away and catastrophic failure occurs. At normal speed, the failure occurred in only a few seconds. Without the aid of the high-speed movie camera, we would never have known what actually happened. It is evident that a narrow land and groove is not the answer. This engineering drawing shows another possibility, a narrow groove for the light feed rate and a wide groove for the heavy feeds. Let's see how it works. Again we start at 16 thousandths feet. The land is too wide. The chip is formed exactly as it was by the flat-topped insert. If we are to break the chip, we must either increase the feed or make the land narrower. Here we have increased the feed to 19 thousandths and the velocity to 525 surface feet per minute. The chip finally finds the front groove, flows down into it, bends up, and breaks. You will notice that the chip does not flow into the second groove, nor does it strike the center island of the insert. This brings up an interesting question. We begin to wonder what would happen if we removed the land from between the two grooves, as shown in this engineering drawing. We would then have a very wide groove with a flat bottom. Here is the result. 525 surface feet, 19 thousandths feet on 1045 steel. The chip breaks exactly as it did in the narrow groove. It flows down and strikes the flat bottom of the groove, bends up, and breaks without flowing into the back part of the groove or striking the center island of the insert. If this is true, we can now design a new groove having a narrow land, a shallow depth, and wide enough so that the chip does not strike the back wall. Such a groove would not restrict the chip at the high feed rates, but would still break it at the lower feed rates. Now, remember how that first chip groove looked? It broke the chip all the way from 16 thousandths feet to 39 thousandths feet. Although at the heavy feed, the chip was very tight, as you see it here. Take a good look and remember how tight the chip is. Then we took it down to 14 thousandths feet. The chip no longer broke, but came off in a long, curling, razor-sharp band which wrapped around everything in sight. Our objective was to learn how to break this chip while at the same time producing a looser chip at the heavy feed. The final engineering drawing shows an example of the design which resulted from the research. It has a narrow land with a very wide groove. The bottom of the groove is almost flat. Let's see what happens at the heavy feed. The dynamometer records the lowest forces with any of the inserts tested. This means increased life at heavy feeds. The chip is loose. It simply drops down against the bottom of the groove, bends up, and breaks. It does not flow into the back of the groove or strike the back wall of the groove. But will it break the chip at the low feed rate? To find out, we took the feed down to the lowest rate of any insert in the experiment, 12 thousandths feet. At the same time, we reduced the velocity to 235 surface feet just to make it a little more difficult for the chip to flow down into the groove. Here you see the result. The chip still flows down, strikes the bottom of the groove, bends up, and breaks. Based on the results obtained from the experimental part of this research and upon the conditions within the experiment, the following conclusions may be drawn. 1. The cutting speed has little effect on the feed range for chip breaking. 2. The groove shape is the main factor in determining the feed range for chip breaking. 3. All components of the cutting force, as well as the resultant of the axial and tangential components and the total resultant force, are affected by the chip breaker groove shape. 4. The lowest feed for chip breaking can be predicted from the groove parameters using the regression model developed. 5. The land width between the cutting edge and the groove is an important factor in determining the effectiveness of the groove. 6. The depth of the groove is not as important as the land width in controlling the chip breaking ability of the groove. 7. The back wall of the groove is not necessary. 8. The chip can, and does, curl off the bottom of the groove.